Hey, what's up everyone? Welcome to the equilibrium section for the 2020 USNCO Local Exam. So this is from questions 31 to 36, and I apologize if you hear something in the background. It's the 4th of July, and people love fireworks. Alright, so let's start with question 31. The endothermic reaction shown below is at equilibrium in a sealed flask with significant amounts of both calcium hydroxide and calcium oxide present. Which action will increase the amount of calcium hydroxide at equilibrium? So we're basically trying to shift the equilibrium. We're trying to figure out what's going to shift the equilibrium such that more calcium hydroxide or more reactants are being produced. Let me get red. All right. Let's go through our answer choices. A, crushing the calcium hydroxide into smaller pieces. That doesn't actually do anything. You're not changing really any intrinsic property of any of the reactants. All that's happening is that when you crush it up, it's going to help the reaction go faster. So the system will reach equilibrium faster, but it's not going to increase the amount of calcium hydroxide at equilibrium, which is what we want. So A is wrong. B, decreasing the temperature of the flask. Well, our reaction was endothermic. That means that your products have more energy than your reactants. So when you add more energy, you produce more products. And the other way goes too. If you decrease the energy, if you decrease the temperature, more reactants will form. So if you decrease the temperature of the flask, more calcium hydroxide gets produced, and that's exactly what we want. So B is correct, but let's go through C and D to make sure that they're wrong. C, adding more calcium oxide to the flask. Adding more of calcium oxide isn't going to do anything because the calcium oxide is a solid. And solids have no impact on the equilibrium expression. So that's wrong. D, adding nitrogen gas to the flask. What that nitrogen gas is going to do is that it's going to increase the pressure. And although that might seem helpful to our case, increasing the pressure isn't going to do anything because the way you're increasing it is by adding an inert gas. The inert gas has no impact on the reaction itself. So it just increases the pressure of the flask, but it doesn't have any impact on the equilibrium. So D is wrong, therefore our answer is B. Alright, let's go to 32. A solution of ammonia, NH3, has pH of 11.5. What is the ammonia concentration? And we're told that the pKa of the ammonium ion is 9.24. For questions like these, it helps to write out the equation, the chemical equation that's happening here, the chemical reaction. What's going to happen is that the ammonia reacts with water, H2O, and I should write the phases. This is aqueous, this is liquid. It's in equilibrium, and it forms NH4 plus and an hydroxide ion. So these are all aqueous, aqueous. All right, let's write the equilibrium expression here because that's also really helpful to do. So since ammonia is a base, we're dealing with Kb. And so the equilibrium expression for this reaction is going to be the concentration of your products. So the ammonium ion and then the hydroxide ion multiplied together divided by the product, the reactants. And only ammonia goes here because the water is a liquid. And remember, pure liquids and solids do not count in your equilibrium expression. And so at the end of all this, we're trying to find out the ammonia concentration. So how are we going to find the ammonia concentration? Well, we can rearrange our expression here, and that's going to give us NH4 plus, I did the wrong thing. That should be a subscript. So NH4 plus times the hydroxide ion over Kb. All right, so what we now need to find is the concentrations of the ammonia, the concentrations of the hydroxide, and we also need to find the Kb for this equation here. Let's first deal with the Kb. So one of the values that we're given is the pKa of the ammonium ion. And the relationship between the pKa and the pKb is that a pKa plus pKb is equal to 14. So if we're told that the pKa of NH4 plus is 9.24, then the pKb of your ammonia, this, is going to be 14 minus 9.24, 14 minus 9.24, which comes out to 4.76. And remember, pKb is just the negative log of your Kb. So if you want to find Kb, you just take that pKb value that you found, and you raise the negative of it to the 10th power. And so your your Kb comes out to 10 to the negative 4.76. That's 1.74 times 10 to the minus fifth. I'm gonna write that here so that I can erase this, and we can find out the ammonium and the hydroxide ions. So your Kb is 1.74 times 10 to the negative fifth. That'll be helpful later when we have to plug this all back in. But for now, let me erase all this, and then we can start finding out the concentrations of the ammonium ion and the hydroxide ion. And you might think that we have to find both of them individually, but there is a special relationship between them. If you look at your ammonium ion and your hydroxide ion, you'll realize that they're being produced in a 1-to-1 ratio. So that means for every molecule of ammonium that's being produced, you also have one molecule of your hydroxide ion being produced. So what that means is that both of these concentrations are going to end up being the exact same. So as long as we can find out one of these concentrations, we can find out both of them. So which one are we going to find out? We're going to find out your hydroxide. And the way you're going to do that is by manipulating the pH. So we're told that the pH is equal to 11.50. And remember, the pH is the negative log of your hydronium concentration. But of course, pH isn't really what we're dealing with. We're dealing with hydroxide. And so what we really want is pOH. And pOH is equal to the negative log of the concentration of your hydroxide ions. So if we can find out what pOH is, we can reverse engineer the concentration of the hydroxide ion. And there's a nice relationship between pH and pOH. So pH plus pOH is equal to 14. So your pOH is equal to 14 minus 11.50, which is 2.5. And so if you want your concentration of hydroxide, that's going to be 10 to the negative 2.5. And 10 to the negative 2.5 is about 3.16 times 10 to the minus 3 molar. And so all of this, we can now take all of this and find out our answer. So exciting. Let me erase all this. It takes forever. I don't know why. And so all we have to do now is plug this into a calculator, and that's your answer. I'm going to do this in red again. I like that red. All right. So your ammonia concentration, NH3, is equal to the concentration of the ammonium ion, which we found out the concentration of the hydroxide. But remember, the concentration of the hydroxide is also equal to the concentration of the ammonium. And so that's going to come out to 3.16 times 10 to the minus 3. And the concentration of the hydroxide is the exact same thing, times 10 to the minus 3. And we should be putting molars, but it's whatever. Over Kb, so Kb is 1.74 times 10 to the minus fifth. And all that's left to do is plug this into a calculator, and the answer comes out to your ammonia concentration comes out to 0.58 molar. And that is, whatever. That's answer choice D. So that's how you go through all of this. You have to reverse engineer the pKa to get your Kb, and you have to reverse engineer the pH to get your concentrations of ammonia and hydroxide. So the answer for question 32 is D. Let's go to 33. At equilibrium, a solution contains 0.50 moles of each cadmium thiocyanate and cadmium tetrathiocyanate. What is the solution's volume? We're given a chemical equation here. We're also given the Kf. The Kf is just a standard equilibrium constant. So we can write this out. So Kf is going to equal, it's just going to be the products, so cadmium tetrathiocyanate over the reactants, cadmium 2 plus, and then you have your thiocyanate, but it has a stoichiometric coefficient of 4, so we raise this to the 4th power. All right. We're told that the solution contains, and also all of this equals to 1.0 times 10 to the minus 3. We're told that all of these reactants and products here, there's 0.50 moles of each of these, and we're asked to find the volume. The way we're going to do this is using the fact that your molarity or your concentration, your M, is equal to moles over volume. So we can rewrite our Kf. We can say Kf is equal to how many moles of cadmium tetrathiocyanate do we have? We have 0.5 moles, and then that's over the volume that we're trying to find. And then we can do the exact same thing for the cadmium and the thiocyanate. So that's 0.5 moles over volume, and then times 0.5 moles over volume, but this is now raised to the 4th power. And all we have to do at this point is solve for V. There we go. And let's see. I'll do it in my calculator. Sorry, I made a little mistake. That should be a plus 3. Plus 3. And as long as you solve for V comes out to 2.8 liters. That's your volume. My bad about that. So your answer is answer choice C. So the answer for question 33 is C. Let's go to question 34. Barium fluoride has a KSP of 1.8 times 10 to the minus 7. What is the maximum fluoride concentration possible in a solution with the barium concentration equal to 5.0 times 10 to the minus 4 molar? So we have barium fluoride, so BaF2, and if we're dealing with the KSP, we're dealing with this equation here, where your KSP, that should be an equilibrium, where your solid is breaking up into ions. So you have your barium 2 plus aqueous, and then you have 2 of your fluoride ions, which are also aqueous. So if you wrote the KSP expression for this, I'll do that in a different color. Your KSP is equal to the concentration of your barium 2 plus times the concentration of your fluoride ion squared. And all of this is equal to 1.8 times 10 to the minus 7. And we're asked what is the maximum fluoride concentration possible in a solution with this concentration of barium. So what we can do is we can first of all, we can isolate for the fluoride. I'll do this in white. So the fluoride is going to be the square root of 1.8 times 10 to the minus 7 over the concentration of your barium. You can just get that from rearranging this expression here. And so we know the concentration of our barium. That is going to be 5.0 times 10 to the minus 4. And so if you do out the math here, so 1.8 times 10 to the minus 7 divided by 5 times 10 to the minus 4, and we take the square root of all that, your concentration of fluoride comes out to 1.9 times 10 to the minus 2 molar. And that is answer choice D. So the answer for question 34 is answer choice D. Let's go to 35. Trimesic acid is a triprotic acid with pK1 equal to 3. You have your pKa values. 100 mils of 0.1 molar trimesic acid is titrated with 0.5 molar sodium hydroxide to give the graph below. What volume of sodium hydroxide has been added at the point marked V on the graph? So this is V. Let me get something other than white. This is V. There's no way to directly find how much sodium hydroxide has been added at exactly V, but we can work around it. The point at which we can find how much sodium hydroxide has been added is at the equivalence point. At the equivalence point is when you have that massive jump. At that equivalence point, your concentration of hydronium is equal to your concentration of hydroxide. And so we can find out our concentration of hydronium and hydroxide using this information here. All right, so we know that 100 mils of 0.1 molar trimesic acid is titrated. And we know that at this point, all of the hydrogens in the acid has been dissociated. So let's find out how many moles of our trimesic acid is in 100 mils of 0.1 molar trimesic acid. So we have 100 mils, which is 0.1 liters. Multiply that by the molarity, so 0.1 molar, and that gets you that you have 0.01 moles of your trimesic acid. But that's not the whole story. Remember, trimesic acid is called trimesic acid because it is a triprotic acid, meaning it has 3 of those hydrogens on it. So if you have 0.01 moles of trimesic acid, then that means you have, I'll do this in a different color, 0.03 moles of your hydronium, so H3O plus. All right, if at this point 0.03 moles of all 0.03 moles of hydronium has been reacted, we need to find out what volume of sodium hydroxide we need in order to have 0.03 moles of hydronium. So we know our concentration is 0.500 molar. And if you ever have trouble with converting molar to moles or like volume, remember what molar stands for. Molar is moles over volume. So since we're trying to find volume, we're gonna need to rearrange this. So volume is equal to moles over your molarity. And so the moles that we're looking for is 0.03 of your hydroxide divided by the concentration of the sodium hydroxide, which is 0.5 molar. That should say moles. And so the volume that we need is 0.03 divided by 0.5, which is about 60 milliliters. 60 milliliters is at this point. That's 60 milliliters. But that's not what the question asks us for. The question asks us for the point marked V. And if you notice, V is just 1/2 of this point here. So V is equal to, I'll do this in a different color. I just love filtering through colors at this point. So V is going to be equal to your 60 mils divided by 2, which is 30 milliliters. And that is answer choice D. So the answer for 35 is D. Let's go to the last one, which is question 36. A solution containing hydrated cobalt, I don't even know what that's called, and then cobalt tetrachloride, and then the chloride ion at equilibrium at room temperature is initially pink. When heated, the solution turns blue. Then when silver is added, the solution turns back pink. Which statements are correct? All right, so let's look at the statements. 1, your cobalt water thing is pink. So cobalt H2O6 2+. What is the charge of the cobalt in this? Well, the water is uncharged, so the entire 2+ charge must be coming from the cobalt. So the cobalt is cobalt 2+. And from your transition metal colors, you should know that cobalt 2+, they don't have pink, whatever. Cobalt 2+ is actually colored pink. So this does make sense. That's true. Formation of cobalt tetrachloride from cobalt water thingy and chloride ions is exothermic. That wouldn't make sense because the reaction only occurs when heated. And so when it's heated, that implies you're dealing with an endothermic reaction because you need to add energy into the system. So this would be wrong. Therefore, the only right answer is 1, so that's A. The answer for 36 is A, and that was the entire section. I hope you were able to learn something. I hope this is helpful. Consider leaving a like and subscribing, and I hope to see you later. Thank you.